Hello everyone, welcome to another interesting lab session on digital signal processing. In today's lab, we are going to see how to design your IIR filters, which is infinite impulse response filters using Scilab. So in our theoretical class, we have seen two types of IIR filters, which are mainly the Butterworth filter and the Chebyshev filter. So in today's class, let us see how we can write a program for your Butterworth filter and your Chebyshev filter. So the problem that we are going to write a program today is this problem that we have solved in the class. Design a Butterworth low pass filter. The passband attenuation is 6 dB minus 6 dB. Stop band attenuation is minus 20 dB. And your passband edge frequency is 2 and your stop band edge frequency is 3. So the unit of this is radians per second. So it's not given. So let me just quickly write. So these frequencies, these are radians per second. So maybe I change the color to that color. Okay. Highlight it. Done. So it is radians per second, this unit. Good. And here we are taking only the magnitude. So take only magnitude. So which means the sign is not. So take only magnitude for this. Okay. So that is your unit. And this is your radians per second, and then here you take only the magnitude. Okay, so now this is my magnitude, which is 6, 20, 2, and 3. So these are the 4 design parameters that are available with me before I write my program. And then these are the formulas that we have derived for your Butterworth filter, which is the deviation, the passband, just the attenuation factor A. So this is my deviation. So this is my deviation, or we can call it as ripple deviation. So I can call this as my ripple deviation. This one I will just call it as my attenuation factor A. Okay. So I can calculate this from this formula. Then coming to the next slide, I have my alpha and beta, which are having this formula: omega s, the stop band frequency, and omega p, the passband frequency. A is the stop band attenuation and AP the passband attenuation. So I get my alpha and beta, and then from alpha and beta I can get the order of my Butterworth filter. This is my natural logarithm. So I can write here, this is my ln. ln means natural logarithm. This is my natural log. In the programs, you have base 10, base 2, and natural log. So we are trying to replicate this. I'm trying to replicate this problem in the program, and then I can generalize it for any values of design parameters. Good. Then the cutoff frequency is given to be between, so it is including, because equal to is there. So less than equal to, greater than equal to. So in this range, you need to pick up, you need to pick a value that will be your cutoff frequency. And I've done something of the same line. I've taken 1.8948 to be my upper cutoff frequency here. And then we need to find the angle, because we have to compute the poles. In order to design the Butterworth filter, you need to know the poles of the Butterworth filter given an order. And these are the equations that will give me the poles of my Butterworth filter. So the n is the order, so which is given as 5. So your n here is my order of the filter, which is computed here. This is my 5. And then sk, this is my pole sk. Omega c, this is the cutoff frequency, right? Cutoff frequency, my omega c is the cutoff frequency. Cutoff frequency. And then I have my theta of k. So theta of k is defined as, what is the theta of k? It is defined as the angle of the poles, angle that your poles make with the origin. So if I draw a line from the origin to the pole, then what is that angle? That angle is going to be theta of k. And this is another theta, that theta of k is also equal to the spacing, the angular spacing between the poles. So that also we can call this theta of k. So all that is covered in the theory. Then we'll come to the next. This is okay. So now we are going to go to the program. So we'll start writing the program for this. So let me get my Scilab started. So this is my Scilab. So what I'll do is, for now, I don't need this. Okay, I need this PDF. So I'll keep this. Maybe I will keep it on this side so that I can use it for comparison. But if the screen size is too small, okay, I'll just introduce this program and then. So design of Chebyshev is next. So we'll go to our Butterworth filter. So design of your Butterworth filter. Good. So these are the given parameters. So if you see the parameters, AP is 6, AS is 20, omega P is 2, and your omega S is 3. So I've just taken this as it is in the question. So we're going to solve this question. All right. So now what I can do is for any filter, you need these 4 parameters, because if you know the Butterworth response, you know that these 4 parameters are more than enough to design your Butterworth filters. So now let me come to this. So see, alpha equation is given here, which is omega S by omega P. My beta is given here, square root of 10 to the power of 0.1 AS minus 1 divided by this equation I have just typed here. Good. So then I get my alpha and beta, and then I compute the order, which is log, that is the natural logarithm in your Scilab, log beta by log alpha, and then we seal. So the seal rounds to the highest value. So the seal rounds to the highest integer. It's slightly different from round. It's slightly different from round off. So we are using seal because when I get an answer of 4.3, I am choosing the order to be 5, and that is done with the help of my seal. Good. So the opposite of seal is floor. So there is another function called as floor, which will round off to 4. So I'll give that example also: floor, seal, and round. So these are the 3 functions we use as on need basis. So I'll just give this example. You can try the others in your Scilab. Seal of 4.3 is 5, whereas floor of 4.3 is equal to 4, and round of 4.3 is also 4. So you all know that. I think rounding is something you must have used plenty. So this is what I this much I can write here, and I'm going with C because that is I have to take the highest order, so highest value after the decimal, that is given by C. Okay, then what is the next equation in my formula? The cutoff frequency. So the cutoff frequency is computed by omega S into, so see this, I have taken, because it's inclusive of these two, I have taken this one. So omega S into 10 to the power of 0.1 AS, that is AS by 10, minus 1 raised to minus 1 by 2 into n. So this equation is this, what is on this right hand side, and that is going to give me the cutoff frequency. Once I have my cutoff frequency, I come to what? The next step in my Butterworth is finding or computing theta k. So where is theta k? Yes, here. So find or compute your theta of k, and that theta of k computation I can do by this equation. Pi by 2 plus 2k minus 1 pi divided by, this is what? I'll just modify this. This is just 2 star ORD n. 2 star ORD n. So 2 into n, that is n is the order. Okay, so that is your, maybe I'll put a bracket so that this is done first before it takes the, just to make sure that it happens in the right. Okay, so yeah, good. So that is your theta of k. So I get k values. So k is 1, 2, 3, 4, 5, because k is equal to 1 to order of n, and so I get 5 theta values. And then what is next? After theta, I compute the poles. So I know my cutoff frequency, I know my theta, I just put it in this equation: omega c into cos theta k plus I into sine theta of k. So that is my poles S1 to S5. Alright, good. So far so good. We are going equation by equation. We are seeing all the equations. We are just converting this mathematical derivation for your Butterworth filter into a Scilab program. And then what is needed? I want you to take a look at this. So this is the textbook form. So the Butterworth filter is given in this manner. So this is the derivation. So the derivation, if I go back slightly, if I go back to the formula, this one. So you see this equation. So this is the equation for your Butterworth filter that we are trying to extract from this program. So which means you have the cutoff frequency at the numerator. So the cutoff frequency raised to the order divided by s minus s1. So you have how many poles equal to the number of order, equal to the order of the filter. So here I'm going to have 5 poles. So the next thing I'm going to do is I found these poles, right? I have to represent these poles because these are my S1, S2, S3, etc. up to S5. Now I want to represent these poles in this form, S minus S1, because I need a polynomial, because this is a polynomial, and that is done with this function. So I convert my poles to polynomial form or to S minus pole form. So S minus pole form, right? So I convert this form using the poly function in Scilab, using the poly function in Scilab. Alright, so that is what this means. So it's going to take each of the pole and it's going to convert it into S minus S1. So I'll run this program and I'll show you the output at each stage. So not to worry about that. So once we get that form, then what I have to do, I have to multiply. So now I have it in this form, S minus pole form. Then I have to take the product. So this is the product. So I have to take, so what I'm doing is I am multiplying. I'm doing a recursive multiplier, setting q equal to 1, and for every increasing k, I'm multiplying this with this. So this is a polynomial multiplication. Good. So that will give me the denominator. So once I have that, then I get this form, right? So I get this form. I can write that Butterworth form, and that is what is written here. Cutoff frequency raised to 5. The order is 5. I'll just zoom on this answer. So this is your textbook answer for the problem, and this is the polynomial. Okay, S5 6. So this is the polynomial that is my Q here. So let us see, and I'll just let's do that. Now let's see these outputs, and then I'll show you how to plot this response for the Butterworth filter. Okay, I'll come to the plotting next. So now I run this program, then I have all these things here. I would like to show what all. So now let me just keep this on this side. So let me first see whether my answers are mapping to the values. Let us see our odd n, that is coming to be 5, right? So our numerical also was having that to be 5. Omega c, so let me see what my omega c is coming out to be. Exactly 1.8948. That is also the right answer. Theta of k, so let me just put what is theta. I get these 5 values. So not possible to see whether theta is right, but let me show you p. So what is my p? See, s, this plus s, this plus s, this plus s, this plus s. So that this is the pole form, s plus pole, s plus pole, s plus pole. Because I think my sk, so let me see what is my s, because I went directly to p. So let me just see. So see my s, so all are negative, yes, that is why. So that is why I get, these are the poles. So these are the 5 poles I get. Let me see whether I have that answer written now. The poles I'm not written, but I'm pretty sure it is given in the textbook. So this is what I've shown here. Okay, so now the P is the S, so it is making into S, and finally my Q is the polynomial. So if you see the final answer, you see the Butterworth polynomial that is given here, S5 plus 6.3. So you see this, because these are the imaginaries are minus 14, minus 15, so they are very small. So that is equivalent to 0. So 6.13, 18.80, 35.6. So it's exactly matching to this polynomial. Alright, so that is how you do your Butterworth filter. So this is the program. So let me just get back to my code of the Butterworth filter. So now I can just plug in any value, so it doesn't matter, right? All your design parameters have to be in these 4, contained in these 4 values. And now the units are important. So if this is not given in decibel, then you need to convert it to decibel by doing that 20 log 10. And if this is not given in radians per second, and if it is given in say degrees then you have to convert it into radians per second. So that unit conversion, so you just have to be, on watch for these units. But apart from that, you don't have to know. You just need these four parameters, and whatever the values, you're pretty much computing everything, and then you get here. So the Butterworth response, I can use the Scilab function, which is butmag order n. You give the order omega c and how many samples you need. You get the plot, and this one can easily be rewritten because this is the program. This is the formula. So what is the formula for the magnitude response of my Butterworth filter? So if I go to the slides, previous slides, I can just show you this one. So this is the magnitude response. So I've derived this in the class. So you see this 1 plus omega upon omega c to the power of 2 order. So this is the formula that is your magnitude response. So if you want, you can use this program, and this one is also doing the same. Your Scilab function, Butterworth magnitude, is also doing the same thing. Okay, so I leave it up to you. And then once you get this magnitude, it is not in dB. So you want it in dB, you do the 20 log n, and then you plot it. Alright, so that is the response you are seeing in your plots here. So you can plot the magnitude response. So now if I just this was the Scilab functions might look how, let us see. I'll close this. Okay, so you need this plot. So let me So for plotting this, I'm putting these two lines. I'll Okay, so this is my, I'm just plotting, see, almost same. So when I plot this, and if I plot this, it's pretty much the same. So new figure, if I open, I think the command is new figure, and let us see if I can plot this also. See, pretty much the same thing. All right, so the range is slightly different. Maybe that is somewhat something to do with this conversion. How they are doing it in magnitude, we have done the same, but somewhat different. But it doesn't matter. So both are giving the same response, just the scaling is different. So you can use either one. You can use this function or you can use this function. All right, so that is your Butterworth. Thank you.